Hey everybody, welcome back to Complex Analysis. So last time we talked about limits and continuity, and then we got into the rigorous epsilon delta proofs. So today we're going to sort of continue along our calculus journey, and if you guys remember back from calculus, what's the next thing you learn after limits and continuity? It's derivatives. So we're going to do the same in complex analysis. We're actually going to talk about how do you define the derivative of a complex function. Okay, so let's just recall really quick our definitions of derivatives from calculus. So recall that we say the derivative of f at x naught is defined to be the limit as x approaches x naught of f of x minus f of x naught over x minus x naught. Now, this interpretation of the derivative, this was coming from secant lines, or the limit of the slopes of secant lines. And just simply, I'll just say secant lines. Because remember, the derivative, at least in a calculus sense, it represents the slope of the tangent line. And how do you get the slope of the tangent line? You have to consider, so here, let me draw a picture for us. Let's say this is our function and we're trying to find the derivative at this point. What we would do, let me choose a different color, is we would start to construct secant lines. And we would get closer and closer and closer to that point, and we look at the limit of the slopes of these secant lines. And whatever that limit goes to, that's what we would call the derivative. So that's what this is interpreting, or this is how you interpret this quotient here. This is really the rise over run, or the slope of your secant lines. But remember from calculus, there's also another definition. If we make, go back to red, if we make the substitution h is equal to, and I got to think about this for a second. If we let h be x minus x naught, okay, then we can take this limit and turn it into probably what you all maybe remember more, and this is the limit of the difference quotient. Difference quotient. Okay, so hopefully this is a quick review on our derivative definition back from calculus. We either have the secant line interpretation or we have this difference quotient interpretation. Now, remember the reason why we had two different definitions was certain functions it's better to use this definition, and certain functions it's better to use this definition. And we're going to sort of proceed the same way. Sometimes we'll be using this one over here, and sometimes we'll be using this one over here. It just kind of depends on the setting or the functions we're dealing with. Now, how do we actually define derivatives in complex land? Very, very similar. So suppose f is a function, and let z naught be an interior point of g. So this is kind of like what we would have in calculus. We never really talk about the derivative at, an endpoint of a closed interval. So we're going to let z naught be an interior point. So let's say z naught, let's say our blob here, this is g, and let's say z naught's right here. Okay, so it's an interior point. So let f be a complex function, let z naught be an interior point, then we define the derivative of f at z naught as follows. And hopefully this looks familiar. So f prime of z naught is defined to be the limit as z approaches z naught of the quote-unquote slopes of our secant lines, f of z minus f of z naught over z minus z naught. Okay, so again, this definition here, we're going to go back really quick. Same definition that we have here in green. Well, similar, except instead of x's, we have z's. And in here, we're thinking about real numbers, and then complex land, we're thinking of, of course, complex numbers. Okay, so if this derivative exists, we say that f is differentiable at z naught. Okay, so again, if this limit exists, remember limits don't have to exist, right? But if this limit exists right here, we would say that f is differentiable at z naught. Now we have some other vocabulary words associated with complex functions and their derivatives. So we say that if f is differentiable for all points in n open disk, so this is an existence thing, some open disk centered at z naught, then we say f is holomorphic at z naught. So what that's saying is, it's kind of a strong condition. It's saying that not only are you differentiable at z naught, but if I draw some open disk around z naught, our function f is derivative at every single point in that ball. Okay, so if that's true, so if there is some ball or unit disk, or I'm sorry, some disk, open disk here, that's centered at z naught for which f is not only differentiable at z naught, but it's also differentiable everywhere else, we would say f is holomorphic at z naught. Okay, that's something we really don't, I guess maybe we can kind of get into differentiability in a calculus sense, but that's something that really we don't have in the complex, or in calculus, I should say. So again, the function f is holomorphic it's holomorphic at z naught if there exists some open disk centered at z naught such that f is not only differentiable at z naught, but it's differentiable everywhere else. Okay. So we say a function f is holomorphic on an open set if it is differentiable at every point in that set. Okay, so this is kind of like if you're talking about derivative or differentiable on a set, it's kind of the same idea. You're holomorphic on a set, an open set, if you're differentiable at every point in that set. And then finally, functions that are differentiable and hence holomorphic in the whole or on the whole complex plane, we call those functions entire functions because they're differentiable on the entire complex plane. There's probably a better reason for that historically, but that's how I like to think about it. All right, so let's go ahead and use our definition to find the derivative of f of z equal to z to the fourth minus z squared. Now, before we jump into the derivative here, I want you to just take a second and think about what would you guess is the derivative of this function. Use your calculus knowledge to think about that for a second. Okay, now what would you think it would be? Well, hopefully you guessed just using the power rule that it's 4z cubed minus 2z. Okay, and you'd absolutely be correct. That is going to be the derivative of this. Okay, sometimes things work really, really nice, just like they did back in calculus and complex land. So let's actually prove this, though. Okay, so the derivative, f prime of z naught, so I'm going to use a different letter here, is equal to, by definition, the limit as z approaches z naught of f of z minus f of z naught all over z minus z naught. Okay, so that was just our definition that we just talked about. So plugging everything into our function here, this is the limit as z approaches z naught of, so z to the fourth minus z squared, so that's f of z, minus, if we plug z naught into f, we're going to get z naught to the fourth minus z naught squared, all over z minus z naught. Okay, so now we're going to do a little bit of rearranging here and distribution. So this is the limit as z approaches z naught of z to the fourth minus z naught to the fourth. Okay, and then minus, I'm going to put this in parentheses, z squared minus z naught squared. Okay, all divided by z minus z naught. Okay. Now notice I have the difference of two squares on the left and the right here, and also over here. Those are the worst stars I've ever written. Anyway, and remember, what's the difference of two squares? So if I have a squared minus b squared, what's that equal to? That's equal to a plus b times a minus b. Okay, so if we use those formulas, we'll get this is equal to the limit as z approaches z naught of, so z squared minus z naught squared, oops, there we go, times z squared plus z naught squared. Okay, so that's a difference of two squares on the z to the fourth minus z naught to the fourth, minus z plus z naught times z minus z naught. So that's the difference of two squares on our second quantity here, all over z minus z naught. Okay, and now we're going to go ahead and use that formula again. Notice we have a z squared minus z naught squared, so again I can break that up so that we get the limit as z approaches z naught of z plus z naught, z minus z naught, times, whoops, actually I guess this doesn't matter too much because it's a plus sign, but z squared plus z naught squared, and then minus z plus z naught, z minus z naught. Now, what was the reason why we did all of this factoring here? Well, now we can cancel out the z minus z naught from both of our terms up in the numerator. So this is going to give us, after canceling these out, we'll have the limit as z approaches z naught of z plus z naught times z squared plus z naught squared minus z plus z naught. Okay, and now we like this because now we can just substitute z equal to z naught into this limit without jeopardizing anything, without blowing up the universe. Okay, so if we plug in z is equal to z naught, or we use the quote-unquote direct substitution property, we'll get 2 z naught from this term times 2 z naught squared from this term minus 2 z naught. Okay, putting these together, what do we get? We get 4 z naught cubed minus 2 z naught. And if, let's just go back to the previous slide, that's exactly what, hopefully you guessed it, should be from our calculus knowledge. Okay, so like we had back in calculus, we could also define the derivative at a point in terms of the difference quotient. Okay, so an alternate definition for the derivative is f prime of z naught is equal to the limit as h approaches 0 of f of z naught plus h minus f of z naught all over h. Okay, and the way we get that is similar to how we would get it in calculus, but this is our, again, this is the limit of the difference quotient here. Difference quotient. Now again, you use either the other definition or this definition. It all depends on sort of what functions you're dealing with. Sometimes it's easier to use the other definition, sometimes it's easier to use this definition. So just keep that in the back of your minds. Whenever you're using these definitions, just kind of think, well, maybe one's better than the other, and sort of proceed from there. All right, so something that's really, really important to sort of get straight is that differentiable, let's not write with the eraser. Differentiable and holomorphic are not the same thing. They're not interchangeable. And remember, the reason for this is just from a definition standpoint. Holomorphic is sort of stronger than differentiable. Remember, holomorphic is you're differentiable at some point, but you're also differentiable at every point in some open disk around z naught, or this point here. Okay, so this would be holomorphic. So it's somewhat stronger, because you're not only differentiable at one point, you're actually differentiable at infinitely many points around that point. Okay. Now to make this more concrete though, your book gives an example of a function that is differentiable somewhere. Okay. So it's differentiable at a point, in particular 0, but it's not holomorphic because it's not differentiable anywhere else. Okay. Now this function in this case that gives us this example is f of z equal to the conjugate of z squared. Okay, so and again, this turns out to be a function that's differentiable at 0, but no place else. Okay, which means it's differentiable, but not holomorphic. Now, just to recall, what is the definition of the derivative? It's the limit as z approaches z naught of f of z minus f of z naught over z minus z naught. So if our function is the conjugate of z squared, this will turn into the limit z approaches z naught of conjugate of z squared minus conjugate of z naught squared all over z minus z naught. Okay, so the way your book shows that this is differentiable and not holomorphic is by using a trick. Okay, so the trick is writing z equal to z naught plus re to the I phi. And secretly what they're doing here, and they're not telling you, they're thinking about re to the I phi as z minus z naught. So then if you take z, you can write it as z equal to z naught plus z minus z naught. Okay, and then the z naughts cancel out, so you do get z back. And then they're substituting for this re to the I phi. Okay, so it's kind of tricky. It's a little algebra trick there. Okay, but in any case, what we do next from that, so keep that in the back of your head, z is equal to this. We're going to take the fraction from our definition of the derivative and we're going to simplify it. Okay, so that's what this work is here. So after a lot of algebra, you can make this look like this. Okay, now keep in mind, if we're looking for the derivative, or we're trying to evaluate the derivative, we're going to take the limit as z approaches z naught. And remember, in limits, you have to have the same limit along any path, right? So here's the issue. Okay, if z naught is not 0, then as we take z, as we take the limit as z approaches z naught, what's going to happen here to our quantity is that it's going to become 2z naught e to the minus 2I phi. Now the reason for that is, and basically this term goes to 0, the reason for that is if z here, okay, which is equal to z naught plus r e to the I phi, if z is going to z naught, that means that this term here has to disappear, right? Now how's that going to disappear? That means that r had to go to 0. Okay, so again, if we're going to compute this derivative limit, that would force r to go to 0, which means that our quantity is going to become 2z naught e to the minus 2I phi. Okay, now this is an issue because now notice that this quantity here depends on phi. Okay, so if we were to travel along a path where phi is equal to pi over 4, then the limit of that path would be 2z naught e to the minus 2I phi. But if we traveled along a path where phi was equal to pi over 2, we would get 2z naught. Whoops, this should be right here, a pi over 4. We would get 2z naught, conjugate of z naught, e to the minus 2I pi over 2. And then clearly, these are not the same number, right? Okay, one's got a pi over 4 and one's got a pi over 2. So what we can conclude from that is if z naught is not equal to 0, then this limit here, okay, our derivative would not exist. Okay, so that's unpacking a lot right there. So take a pause if you need to and kind of go over that. But in any case, here's a function that's not differentiable at any place that's not 0. Okay, now to prove that this function is differentiable at 0, you actually need another exercise, 2.5, which we're going to prove part of in a second. But the general gist is if z naught is equal to 0, then our difference quotient here just becomes z, the conjugate of z squared over z, which unfortunately those don't cancel out very nicely. And then eventually you can show that this is equal to 0 by showing that this is equal to 0. Okay. Now we're going to go ahead and prove that, and I'm going to have you guys prove the other direction in class. So to get this, we need to show, and this is actually a theorem, okay, if the limit as z approaches 0, or z approaches z naught actually, doesn't actually matter if it's 0 or not. If the limit of the absolute value of f of z as z approaches z naught is equal to 0, then the limit as z approaches z naught of f of z is also equal to 0. Okay, so let's go ahead and prove this really quick. This is actually an if and only if, by the way. So if we had this, we actually get this as well. But I'll have you all prove that on your own. And it actually follows very similar to what we're about to do anyway. So in any case, let's go ahead and prove this. So proof. Okay, so suppose the limit as z approaches z naught of f of z is equal to 0. Okay, so we're going to try to show WTS the limit as z approaches z naught of just regular f of z, so not the modulus of it, is also equal to 0. Now, how do we prove limits, or what do we use to prove limits? We're going to need the epsilon delta proof. So let's let epsilon be greater than 0. Okay. Now, since we know that this limit right here is equal to 0, we get a delta. Okay. So since limit as z approaches z naught of f of z equals 0, there exists a delta greater than 0 such that, okay, if the distance between z minus z naught is less than delta, then Okay, now here, this is where it gets a little bit tricky. Well, not too tricky, but then the distance between the absolute value of f of z, okay, which is this part, minus 0 is less than epsilon. Okay, now this is the cool part, because what is this quantity right here? This is just the absolute value of the absolute value of f of z. I should say the absolute value of the modulus of z is less than epsilon, but the absolute value of the modulus of z is just the modulus of z. You can't make something that's positive. Well, if something's positive already, it's going to be positive anyway, or already. So we get this. But this is exactly what we would want to show if we're trying to show that the limit of, whoops, should circle this one. If we wanted to show the limit as z approaches 0 of f of z is equal to 0. Because what we need to show, we would need to show that the absolute value of f of z minus 0 is less than epsilon. But that's exactly what this is saying right here. So it's kind of a neat little proof. It just kind of follows out really, really nicely using epsilons and deltas. Okay, so let's get into some basic properties of derivatives. Like in calculus, we have some really, really nice properties of derivatives, which we're going to talk about. So suppose f, that was fast. Suppose f and g are differentiable at some point z and c, and suppose that h is differentiable at g of z. Okay, then we get the following. So the first rule says that if you take the derivative of f plus c times g, you can sort of distribute the derivative over that sum. Okay, now this is kind of a twofer. If you guys remember back in calculus, derivatives, they distribute over sums and differences, and you could always pull constants out, right? Okay, so that's what this statement here is saying. It's saying actually sort of a 2-in-1. Not only can you pull constants out, because that's what was happening in the second term here, you can also distribute derivatives over a sum, and it also works for differences. I know your book doesn't say plus or minus, but it actually works for that as well. Part B here is our classic product rule. So the derivative of f times g is equal to f prime g plus f times g prime. Part C here is the quotient rule. Okay, the derivative of f over z is equal to f prime g minus f times g prime over g squared. We have the power rule. Okay, so the derivative of z to the n is equal to n z to the n minus 1. Okay. If you're differentiable at a point, then you are continuous at that point. That's what part E is saying, which again, that's another calculus result. If you're differentiable, you're continuous. Differentiability is really, really awesome. You get a lot of neat things with it. And then finally, F is our chain rule. So the derivative of h composed with g is equal to h composed with g times the derivative of the inside, g prime is z. So let's go ahead and prove the quotient rule. So remember, the quotient rule says the derivative of f over g is equal to f prime g minus g prime f all over g squared. Okay, so let's prove that. So proof. Okay, so by definition, the derivative of f over g of z, and now we're going to use the difference quotient definition. This is equal to the limit, as now h approaches 0, of f of z plus h over g of z plus h minus f of z over g of z, all divided by h. Okay, so that's our definition of the derivative. Now after simplifying our numerator, okay, so subtracting these two fractions, we're going to get limit as h approaches 0 of f of z plus h, g of z, minus f of z, g of z plus h. And you can sort of see the top part of our quotient rule formula appearing here, divided by g of z plus h, g of z, all divided by h. Okay. Now here's where we get a little bit tricky. So first of all, and I don't want to rewrite this whole thing, since we're dividing this whole crazy fraction by h, I'm just going to move the h down here, because remember, if you divide by something, it's like multiplying by the reciprocal. Okay, now that wasn't the trick. The trick is the following. So we're going to take our numerator there, and we're going to add and subtract something. Okay, so we're going to add f of g, g of z, and then if we add it, we're going to have to subtract it as well. Now you might be like, why the heck are we doing that? You'll see. You'll see. You'll all see. Okay. Now what we're going to do is we're going to rewrite this fraction. So pause if you need to, but we're going to rewrite this fraction by first, we're going to factor out g of z from these two terms. Over in these two terms, we're going to factor out f of z, and then we're going to somehow split our fractions up so that we get nice derivatives. Okay, so we're going to get limit as h approaches 0 of, so g of z times f of z plus h minus f of z. So that was from that first term, minus f of z times g of z plus h minus g of z all over h times g of z plus h times g of z. I don't know why I added an extra set of parentheses, but we're going with it, everyone. We're going with it. Okay, so now we're going to be really tricky and we're going to rewrite things. So this is equal to the limit as h approaches 0 of 1 over g of z plus h times g of z. So I'm pulling out these two things. Okay, and now we're going to actually split apart our fractions up here and rewrite this as g of z times f of z plus h minus f of z over h. Okay, so that's from that first term there. Then minus f of z times g of z plus h minus g of z over h. Okay, now why do we like this? Well, what's the limit as h approaches 0 of this quantity? That's going to turn that into f prime of z. Okay, what's the limit as h approaches 0 of this quantity? That's going to turn that into a g prime of z. And what happens as h approaches 0 of this quantity right here? We're going to get, well, just g of z. Okay. Now, all these other factors, g of z, f of z, those don't matter because they don't have h's in them, right? So they sort of come for free. So sort of filling in the gaps, what are we going to get? We're going to get 1 over g of z times g of z here. So that'll be g of z squared times f prime of z times g of z minus f of z, g prime of z, and rewriting this, we get exactly what we want. We get the quotient rule that we know and love back from calculus. Okay, so we're going to really quickly talk about a property of holomorphic functions, which is pretty cool. And that's conformal. Okay, so suppose f is holomorphic at some point a and c. So let me give you a little picture here. So I don't know why I drew a blob because I guess I'm used to it, but let's say this is a. Okay, and suppose we have a function that's holomorphic at this point. And remember, holomorphic means that not only are you differentiable at a, you're also differentiable on some open disk around a. Now suppose that we have two paths, gamma 1 and gamma 2. That are going through A. Okay, so maybe they're doing something like, here's gamma 1, and then maybe gamma 2 is doing something like this. Boom, something like that. Okay, so if you consider the angle that these paths are making at A, we'll call that theta, you get a really, really cool result. Okay, and the result is the following. So if you plug in, or if you look at the image of gamma 1 and gamma 2 under f, okay, then what's kind of cool, or the cool result that we get, is that if you were to look at its image, trying to get a different color here. If you look at its image, let's say here's f of a, and let's say the image, meaning what happens to gamma 1 after you plug it in, let's say gamma 1 looks like maybe something like this now. And then maybe gamma 2 does something like this. Actually, maybe something like that. Don't like that. Whoosh, something like that. I don't know. So let's say this is our f of gamma 2. The green here is f of gamma 1. Okay. So what this proposition is saying is that if you consider the angle that these two paths now, f of gamma 1 and f of gamma 2, are making it at A, what's really, really awesome if you're dealing with a complex holomorphic function is that it actually preserves this angle. This angle is actually going to be the same as the angle that you started out with here. And that's what it means to be conformal. Conformal functions are functions that preserve angles in this way. And that's something that is really, really cool. And I don't want to say unique, but it is a property of holomorphic functions as long as your derivative is not 0. Now, if you want a proof of that, go ahead and read your book. But we'll go ahead and skip that for now. But anyway, that's a really, really cool result of holomorphic functions. All right, so next time we're going to get into one-to-one onto and then the inverse function theorem.